Hey guys, welcome to Code Decode. In this video, we are going to cover some top microservices scenario-based interview questions for 5+ years experienced people. So let's get started. Also, if you want to implement an end-to-end project with microservices, Angular, and all these technologies like AWS, Sonar, Docker, Jenkins, Argo CD for deployment, CICD, RESTful web services for communication between microservices, and many more things for end-to-end project, you can have a complete implementation given at our Udemy course. Link will be given in the description bar below. Now let's get started and cover some scenario-based interview questions for 5+ years experienced people. How would you design and implement a microservice? So whenever a project is getting started, the first thing is the requirement gathering. Now you know that whenever we have a new project coming into our bucket, we might not have end-to-end every requirement in our plate given by our clients. In that scenario, how will you directly decide what should be the microservice bounded context? If you have an e-commerce website to be designed, how would you decide you should have payment microservice, order microservice, user microservice, and so on? There might be changing requirements now and then by the client, and your bounded context might change now and then. And hence your microservices context, their boundaries will also change. So whenever you are asked to implement a microservice architectured application, you should always start with monolithic one. So what we should do is to start with a monolithic application, put everything which is bare minimum requirement given by the client, create a minimum viable product, show it to the client. When you have the proper approval that yes, this is what the client needs, then only think about microservice architecture. So the first thing is always start with monolithic and create a minimum viable product. Second is, now you should start planning how to implement a microservice. So now you should have your team organized in a perfect way. So you should have proper number of development team, DevOps team, testing team, and many such teams. Now once you have organized your teams in the perfect way, now you can split your monolithic one to the microservice architecture. So by till this point, you are actually planning everything and building the blocks for creating a proper microservice architecture with proper requirement in place, with proper team in place who are going to develop those microservices. So the third part is to split your monolith one now to the proper microservice architecture. So how will you do that? You will define proper bounded context. Like, this is going to handle the orders for me. So that is order microservice. This microservice is going to handle all the product catalog for me. That is product microservice. So you have to divide each and every major requirements into bounded context so that you can share the data between them and handle the duplicate data efficiently. Now, when you have multiple microservices in place, the important part is how will you communicate between them. So while splitting only, you have to decide, you have to use synchronous communication between these microservices or asynchronous communication or the combination of both. So you can have RESTful communications with smart endpoints and dumb pipeline principle. That is, you should have the proper APIs and microservices in place to handle all the business logic and data transformations. And for the RESTful APIs, use the HTTP pipes, who are not going to do any business logic, just going to transfer your request from client to server. So that's the way for communication synchronously. Or you can have asynchronous communication using queues like RabbitMQs, ActiveMQs, Kafkas, and many more such things. So now when you have done these things, you can have the service interactions with each other. You can have your data in place, like you have to decide you want to have one database per microservice or you have a common database for all the microservices, which is not a good idea though. If there is a need for that, you can go for that. So in the third step, here is the major task to be done. When you have to decide the bounded context, you have to decide the way how your microservices communicate. You have to decide how many database per microservice has to be decided. So this point is very important. Now when you have every microservice in place, you have proper team working into these microservices, you have the communication properly done. Now the fourth step is you have to make sure that your microservice architecture do not fail. So whenever these microservices comes in production environment, most of the time if one of the microservices fail, multiple microservices might get affected because of one of the microservice failure. So you have to focus on resilience, service responsiveness, recovery, and message handling. All of these can be done with multiple inbuilt integration tools like, for example, Haze, Streaks, and many more. So now when everything is done, you have to plan for your failure management so that you provide a proper responsive good performance application to the client, and they do not get internal server error 500 exception and such exceptions when your microservice is down. Now, when you know that your microservices will be available 24/7 without any failure, now you have to emphasize on your testing part. Because now your testing will not be simple unit testing with JUnits and everything. Why? Because your logic is divided across multiple applications, multiple microservices. So how will you test the whole system end to end? How will you make sure that, yes, when you place an order, a payment is done, but if your order is cancelled, a payment is reverted? How would you test this end to end flow with code written in different microservices? The way to do that is the system integration testing. So integration testing using BDDs are the ways to manage the testing between multiple systems. So testing becomes a very complex task when it comes to microservice architecture. Also, remember to use CICD for deployment process, because deployment for monolithic is very easy. You can deploy it one way. But when you have multiple microservices, deploying each and every application standalone by yourself is a very difficult task. By making it automated using CI/CD, it reduces the risk of release failures like prod failures, and you can actually focus on just development and running your application rather than remembering what wrong you have done while doing the manual production deployment. Also, continuous delivery makes sure that you have all the acceptance tests passing before the production is live, so that you actually passes all your unit test cases, all your BDDs and everything is passing before you are on to the production. So these are the ways you always have to prefer while implementing a microservice architecture. Now a next scenario based question is, you have microservice architecture, you have monolithic architecture. Explain the scenarios and situations where you will prefer microservice over monolithic architecture, or you will focus more in developing monolithic one rather than moving to microservice architecture. So which is better in which scenario and why? Now first, when you have a monolithic architecture and you want to move to microservice architecture, the great example is e-commerce website. Now you have an e-commerce website with millions of users. Your application is built on the monolithic architecture. But when the business grew, more and more people and users comes into your application and starts ordering and performing multiple tasks. Now, suppose there is some sale going on your e-commerce website. There, the load increases such a lot. Then how will you handle n number of users simultaneously coming to your platform? You have to make it more scalable. So microservices can handle scalability much more efficient than a microservice one. Secondly, it will provide you more flexibility for technology choices. Now, for example, you are in a market and you're developing a particular application like e-commerce website. Now, you do not get all the programmers with Java development. You might get some with .NET one. So you can make sure that one of your product microservices is on Java, your order microservice is in .NET, and they both are interacting with a common protocol, that is HTTP. That is very much possible. So flexibility is something which is given by microservices to you. Thirdly, development velocity. Now you have multiple feature enhancement coming to order service also, payment service also, order service also. How will you manage all these by just one single team? Rather, is it not better that each team works independently on multiple enhancements rather than doing it in a streamlined process? Then in the multiple parallel ways, you can develop and release multiple enhancements simultaneously. So with microservice architecture, your speed also increases. Also with the team structure, the team is responsible for end-to-end development of only one single microservice. Thus, they will have end-to-end complete knowledge for their particular microservice. So it's better to move to microservice architecture with different teams segregated with their different strength in each microservice. Also complexity. If you have everything in one single application, like payment is also there, order management also there, food product catalog is also there into it, then it makes it much more complex and unable to easily understand the code. So the complexity also increases with the monolithic architecture, which is reduced with the microservice one having completely segregated and readable code. And lastly, maintenance. Now, if you have a monolithic architecture and your one of the part fails, like for example, your payment is getting failed, then the person is not even able to see your orders or not even able to see your product catalog. In that case, even when he is not going to use the payment service, still the basic view of your orders will also not be available to the client, which is so bad. So maintenance of monolithic is very difficult. While in the case of microservice architecture, If your payment service fails, but your other microservices like product catalog service, order service, everything is working fine, then the complete system doesn't go down. Only a sub part of that particular whole system goes down at a particular time, which gives a better user experience. In that case, also microservice architecture is preferred. Now, the scenarios where monolithic architecture is preferred over microservice architecture, which is very rare, because there are very few scenarios where monolithic is better than microservice architecture, because everybody needs modularity. But there are still some situations where modularity is not that much required. For example, in a bookstore. Now, what do you do at a bookstore? You just select a book, read it then and there, and put a review. The very minimal thing is what you are developing. So here you have very limited complexity. Basically, your online store is very much straightforward. You don't have multiple things as the requirement into that particular application. Now, breaking into multiple microservices will not produce rather advantages, but will actually add complexity to your simple requirement. So when you have very simple requirement, then do not go for microservice architecture, because it will add complexity. Also, sometimes the microservice architecture do reduce the speed also. That is when if you have multiple microservices, now if you want to change something which spans across multiple microservices, for example, there is some change which actually impacts my order service also, my product service also, my payment service also. Then first one team changes, then the second one, then the last dependent team changes. So first you have to plan the dependent changes, then you have to deploy the dependent changes in the particular order. So this actually reduces the speed when the change actually spreads across the whole microservices. In that case, monolithic is advantageous. Also, when you have a poor client, basically they do not have money to give you. So when you have the resource constraint, you do not have money, you cannot actually have proper resources for your development, deployment and maintenance. Like they do not have money for your AWS. They cannot afford that. In that situation also, you have to go for monolithic one. When you have limited resources and you cannot invest in the architecture as it is not cost effective and feasible for you. Next, performance. Microservices for sure does introduce some performance overhead, and that is because inter-service communication. If you have everything in one particular application, you do not have to call another service, wait for its response and come back. So this actually adds some latency and performance impact on your application. So when you don't want that, go for the monolithic one. Also, if you have a very small team or you have suppose a single developer. Now, if you divide it in multiple microservices, he'll be so confused like which code is written in which particular microservice. He will be end up working in multiple applications simultaneously, adding up so much overhead to that single developer. So when you have a constraint on the team size, you have a small team, and giving all these applications to one single developer is such a bad idea. So when you don't have the proper team size, you have less resources in terms of team also, then also don't go for microservice architecture. Also, transitioning to microservices actually have a learning curve. You have to understand how inter-service communication works, how pipelines will be working, how data consistency will be working. In all these situations, you have to have a learning curve. When you do not have that time for the learning curve for your team, do not go for microservice architecture. Stick to the monolithic one and give the things on time to the client before an escalation comes to your part. So the situations are very different for monolithic and microservice architecture. You might want to go for microservice architecture, but you do not have proper resources, you do not have proper team, you do not have proper learning curvature time. In all those scenarios, you actually should not go for microservice architecture. Stick to monolithic one, give minimum viable product that is required by the client and complete your task then and there. Now the next question can be, how do you make sure a microservice based application can handle more users as it becomes more popular? Now for example, you have created some application, you have made it live. Initially, with your client, you have very few users coming to your application since it's a very initial phase of your product. But as and when your product gets more and more popular, for sure more and more users will be attracted to your application. In that case, for example, in normal days, the Flipkart, Amazon, these apps will have less users in a normal day. But when you have the great festival sale coming up, you will have more and more users attracted to Amazon and all. Then how will you handle n number of users simultaneously hitting your application and increasing the load on your instances? How will you handle that? So what you can do is you can load balance your application. So when you know that more people are coming to your application, you can load balance. You can have multiple instances of your services, and rather than overloading one single instance, you can rather implement a load balancer and evenly distribute all those users among multiple instances so that you have better user experience. They do not have to wait for your response from your server because you will have multiple servers responding to multiple users simultaneously. This prevents overloading of single server and ensures the better performance and better user experience to your users. Next is horizontal scaling. Now, what is horizontal scaling? That is adding more and more instances to your service. And without the horizontal scaling, you cannot do the load balancing. So obviously, horizontal scaling is required when the user load increases on your application. Then auto scaling. Nowadays, most of the cloud providers provides more and more auto scaling feature to you. That means they automatically add and remove instances in the real time to optimize your resource usage and costing. So what they do is when you have the sale going on, you have more users, they automatically add the more and more replicated instances to your application. And when the sale is done, they will remove those resources so that you are not charged for those resources which are empty and not serving any user, but still is there on your system. So that's auto scaling. Then caching, you can implement caching also on your services, which will help you access the data very quickly and you do not have to wait for the response from the server. You can have your own cache maintained and serve the static data to your users quickly. Next is database scaling. Now there can be a case that you will have database also to keep your data for your application. If you have multiple instances but only one single database, then multiple users will have to wait to access that single database. Better if you have done the horizontal scaling, also focus on database scaling, because many a times we focus on making the instances scalable, we forgot to scale our database, and that is where the bottleneck comes. The bottleneck caused because of database will actually reduce your performance. So if you're focusing on instance scaling, also focus on database scaling. Also, you can do the asynchronous processing. Many a times when we start creating an application, we do the REST API implementation or the synchronous communication between services. But to increase the performance, to ensure the quick response, you do not have to always wait for the response from your service to give the response to the user. For example, when you have placed an order, you have to send an email. So rather than waiting for the proper email sending to the user and getting the response that the email has sent successfully, then telling the client that yes, your order is successfully placed, you place an order, you put it in an asynchronous queue, Kafka, RabbitMQ, ActiveMQ, any of the queue, and just send the response to the client that it is done. Because at the end, the email will for sure be sent if the service is up and running. In that case, you do not have to do the waiting for the email procedure. You rather quickly send the response to the client, ensuring that you have better user performance by doing the asynchronous processing of emailing. Now, the next question will be, how do you handle data consistency in a microservice architecture? Now, let's first understand what the question the interviewer is trying to ask you. What is data consistency? I'll give you an example. You have an e-commerce website where you can place an order, get the payment from the client, and place an order successfully and send an email to the client that your order is successful. Now, the three microservices that you can barely see here is that you have an order service to take an order, you have an email service to send an email, and in between you have a payment service to get the payment. You can place an order from the order microservice, then you take the payment from the client, and when the payment is successful, you send an event that order is successfully placed and you send an email. Now, in this case, if the payment is not successful, if the balance is not sufficient in the card or something wrong happened with the payment, how do you make sure that data is consistent? That means if the user has placed an order and the payment is not successful, then you should roll back the order confirmation done in the order microservice. If the payment is failed, then order also has to be cancelled. How do you make sure this data consistency? So you have multiple ways to handle data consistency in microservice architecture. But always there will be the balance between consistency and performance. If you make sure that your data is always consistent, then for sure the performance will be lagging. And if you want better performance at any cost, then for sure your consistency will be lost somewhere for some time. We have a way of synchronous communication. When you place an order, the order service will give a call to payment service that get a payment, and till then the user will be waiting that order is in process. That is synchronous communication. You will not get the immediate response if you have the synchronous communication through REST APIs or gRPC. But when the response comes that order is being placed successfully, that will be the case only when your payment is successful. That is synchronous communication. So here you can see that there is very strong data consistency. This will never be the case that you will get a message that order is placed successfully, but the payment is failing, because your order placed successfully message will come only when the payment is successful. So that's synchronous communication, and that is having a very high data consistency. But there is a problem. Your user will be waiting, having a message, order is in process, until the payment is not done. That is synchronous communication, which is very sensible also. You should not get order placed successfully unless you have not the payment successful. Second is asynchronous communication. Now, if you have placed an order successfully, you have also made the payment successful. Now you have to send an email. So do you want to show your user that order is processing when you want to send an email but the payment is successful? No, you should not keep your user waiting for the email processing. What you can do is, when the payment is successful, just send the response back to the client that your order is placed successfully. But do not wait for sending an email to the user also. What you can do is, you can send an email through the asynchronous communication. So first you place an order through order microservice, you do the synchronous communication and wait for the payment. When payment is successful, do not wait for the user to have the email sent successfully. You can do it asynchronous communication with the email service and send the response to the user, your order is successful. Later on, put a message or email message to the queue like ActiveMQ, RabbitMQ or Kafka, and in the background send an email to the user. So this is how you do the asynchronous communication. But you can see that if you would have waited for the email procedure, then your user will be waiting for a long time, and that is bad performance. But in asynchronous communication, you send the message to the queue and send the response to the user for the quick response and order is successful. That's how you get the better performance, but you lag in the consistency. How the consistency is lacking? Because email is not yet sent. There might be a case that your microservice gets down. Though even the order is successful, your email is not getting sent to the user. That is how your consistency is breaking. Your order is success, but your mail is not sent. But as soon as your microservice gets up and running, the email microservice gets up and running, eventually you will get the consistency. Eventually, after some time, the email will be sent to the user. So temporarily, there is some consistency lagging in the order successful screen and in the email notification. But later on, you will be getting there. The third is CQRS, that is command query responsibility segregation. Here what you do is you segregate your command or updation to the data and your query in two different databases and microservices. So what happens is, whenever user come to query, one database and one microservice will always respond to it. But whenever a request comes to update the data, delete the data, add the data, that is a command for the data, then a segregated microservice and database will be responsible for it. And later on, whenever the user comes to query something, a query database will be responsible to respond, and whenever a command comes, a command service will be responsible for response to the user. But how the consistency is maintained? There is always a communication between the command microservice or a query microservice. They interact with each other with a synchronous or asynchronous communication. Usually it's asynchronous communication done through the queues. There might be a case that when a query comes from the user, it might get some stale data when you are doing the asynchronous communication between query microservice and command microservice. That's the way to handle the consistency, maintaining a proper, better response to the user. Also, you can have the event sourcing, means that whenever a data change comes, it is captured as a sequence of event. That is event sourcing. That means whenever first an order comes, then a request for the payment comes, then the request to the email sending comes. All these three comes as an event, 3 different events. And whenever your payment fails, then you roll back to the previous event also. That means when you create an event, that place an order. Then you create an event, ask for the payment. If the payment fails, then you roll back to the previous event and says that also cancel the order because the payment has failed. That's the series of event you can manage for the data consistency. Then you can have the distributed transactions also to maintain some data consistency in the microservice architecture. But remember, whenever you do the distributed transaction, what you always do is synchronous communication. For example, in the 2PC, you always do the synchronous communication. In that case, you always have less performance but a best data consistency because it is synchronous. But when it comes to Saga design pattern, you try to implement it using asynchronous communication using Kafka, ActiveMQs, RabbitMQs and queues. So you have sequence of local transactions in the Saga design pattern where each of the data maintains its own data consistency, but if anything fails, you roll back the local transactions. That is the Saga design pattern using the asynchronous communication. We have created a complete separate video on Saga design patterns and CQRS. You can get the link in the description bar below for better understanding of how local transactions and how rollback happens in the Saga design pattern. But this always uses asynchronous communication, so you have better performance but less and temporary data consistency. How? Because initially you have one transaction done saying the order placed successfully, but when payment is failing, then you have to roll back and say sorry, your order is cancelled because your payment has failed. That is Saga design pattern with the local transactions and rollbacks. Also, these were the ways to maintain the data consistency. But there must be a way to make sure that your data is actually consistent across microservice. That can be done using monitoring and logging. So you have to monitor and properly log and detect and diagnose your data consistency issues early. You have multiple distributed tracing tools, centralized logging tools to handle and find out anomalies in the data across multiple microservices. So when you have proper monitoring and logging, it makes sure that yes, your data is consistent across microservice. But what happens if the monitoring and logging says your data is inconsistent? Then you need conflict resolution. So there are multiple strategies to handle the conflict if they arises in the data in different microservices. They may involve time-based conflict resolution, or even in some cases you have to intervene with a proper human intervention. Say suppose if you have a production having the conflicts, then you need a human intervention to resolve that conflict in the data so that the users are not impacted. So these are the ways to handle the data consistency. This is the way to monitor and log whether data is actually consistent. But if the logging says data is inconsistent, then you should have a proper conflict resolution to make sure user is not affected. So that's the way to manage the data consistency. Now, since you have used a 2PC, you have used a Saga design pattern, the next question may come to you is, what is the difference between Saga and two-phase commit? And which will you prefer in which situation? So the main difference between two-phase commit and Saga pattern lies in the way these actually work. The 2PC works with the synchronous communication while Saga works with the asynchronous communication. Now for that, first you need to understand Saga and 2PC. 2PC works with the synchronous communication where there is one coordinator. Say order service is the coordinator. The payment service and the email service becomes the participants. The order microservice sends a prepare request to payment service. When the payment service says yes, payment is successful, you will have a vote to commit or vote to abort based on the payment is successful or payment is unsuccessful. In both the cases, the order microservice will be as a coordinator will be waiting for the response from the payment microservice. So this is a blocking scenario. That is a synchronous scenario. So the way how the two-phase commit in Saga works is different. Saga has local transactions while the two-phase commit has the messages going here and there as a prepare and the vote to commit or vote to abort. For if you want me to cover the two-phase commit in detail, just let me know in the comment section. I'll create a very separate video for this, and for the Saga design pattern, a complete separate video is already present on the channel playlist. The link will be given in the description below. Now, to understand what is the difference between two, you should understand that two-phase commit works with a synchronous communication, where until the payment is not done, the order service will be waiting. But if you would have used Saga design pattern in the e-commerce website, then you will see the asynchronous communication, where the user will see the order is placed successfully and later on the payment is processed, which is not a good case. But if you have used Saga design pattern, this is how it will be working. And if the payment later on gets failed, then you will get a notification that since your payment was failed, your order is now cancelled. So even though you have get the order confirmation, later on you will get the notification for order cancellation also. That is the rollback of the local transaction. That's asynchronous communication. Two-phase commit, because it is synchronous, it is blocking. Blocking means if in any case your payment service is down, then your order service will not get the response for your prepare message. You will not get vote to commit or vote to abort. In that scenario, you will have a blocking situation. But when it comes to Saga design pattern, it's a non-blocking situation. When it comes to consistency, two-phase commit, because it is synchronous, it is very consistent. You will get the order confirmation only and only when the payment is successful. But in the Saga design pattern, if you will get the order confirmation as soon as you place an order, but your payment is successful or not depends upon the payment microservice. If it is successful, your order confirmation message remains as it is. But if it is unsuccessful, you will then have a rollback. That means you will have the notification your order was cancelled because you didn't do the payment. That is, eventually your system will be consistent, but at that point of time, you will have a data inconsistency because you get a message of order confirmation, but your payment is yet to be done. If the payment is successful, your system is consistent, but it is unsuccessful, you become in an inconsistent state of having the message of order placed successfully, but the payment is unsuccessful. Eventually, you will get the consistency. That's Saga design pattern. The two-phase commit adds complexity because you need one transaction coordinator. You will have one message traveling of synchronous communication that prepare. You will have messages like vote to commit or vote to abort. So lots of complexity is added by two-phase commit, while that is not the case when it comes to Saga design pattern. It is usually less complex than 2PC. The two-phase commit also adds performance overhead because the synchronous communication is needed and additional communication and coordinator is required, which is not in the case of Saga, and hence it's better in the performance because it is much more simpler. But the best part of two-phase commit is it is a very strong data consistency, but it comes with the cost of performance overhead. When it comes to Saga design pattern, you have a temporary inconsistency that I have told you already. When you have the order placed successful message but a payment is unsuccessful, then you have a temporary inconsistency, but because of this you have a better performance. So it completely depends upon you which to use when. Whenever it comes to e-commerce, I'll always prefer two-phase commit or distributed communication. But when it comes to emailing system, then Saga pattern is also good. It depends upon your requirement. You want to use two-phase commit with synchronous communication or asynchronous commission in Saga design pattern. So that was all about interview questions for 5 years experience in microservices. If you want more such questions for 7+, 9+, or the architectural level questions, just let us know in the comment section. We'll create more such interview questions for you. Thank you.